Welcome to this is like the pinnacle, right? Because we talked about Legos. You built the base, and honestly, Calc 1 and Calc 2 are they're pretty cool things. But we learn these things, and we never get to use them to their full potential and see what they can really do for us. Calc 3 doesn't do all of that, but it gives us a really good insight into why you learned a lot of the Calc 1 and the Calc 2 stuff that you just did, like integration techniques. Like, okay, fantastic, what we're doing, I don't know, area under a curve or something like that. Yeah, that's right. But we can use it for a lot more stuff. And how we get to that more stuff right now, the next level of our base. So I mean, we built Calc 1, we built Calc 2. Now we have this kind of like RAM part we're working on called vectors. We're going to learn about vectors so that we can come back and flesh out all of the rest. Of calculus 3. Why we need vectors. Number one, it's really hard to describe motion in 3 dimensions if you don't have them. So vectors allows us to do that. Also, even in 2 dimension, sometimes, I mean, not sometimes, a lot of the times, just a speed or just a direction isn't good enough for it. For instance, if we're driving down the freeway, we go, hey, where'd you go? 60 miles an hour. What are you talking about? I mean, where did you go? I was going 60. Great. 60 where? 60 north, 67. That's going to make a difference. Where you end up in Sacramento after a couple hours or Los Angeles is going to make a difference. So we don't like to just describe direction. We don't like to just describe speed. We like both. We want to say we were going north, we were also traveling at a speed, a magnitude of 60 miles an hour. Or we were going east and we were going 30. Or we changed direction in somewhere. We got a couple vectors going on. That's the idea. That's why we have this vector idea. Now,
Does it work? Yeah. Let's actually put my beautiful face on the camera. Why not? Yeah, let's.
when we talk about vectors, if this is your first time ever seeing vectors, I'm going to try to break it down to show you what we're talking about. Here's anybody's first time seeing vectors? Okay, that's good. And you can be honest in this class. Yeah, how many first time you've ever seen a vector before? Show hands. Never, it's a few of us. Here's what vectors have. Vectors are this way to describe motion, way to describe a particle, way to describe even a function later on.
So, best way to learn math? Question mark. I need to stick to like a particular book. Best books on calculus 3. Should I always stick to the same author? Question mark. Pretty sure, right? And no, you don't have to stick. Why when mixing is better? Mixing books can help with author explanation clicks. Yes, of course. Sticking to one book can reduce confusion because notation is. What about publications? Question mark. If you're like publishing something, no. Anyways, okay. Best Calc 3. Unfortunately,
Many calculus
everything you just have to like learn it by book, and that's the
and
hard realization that I've come to, which would have saved me some time reading like linear algebra and all of that, right? I was okay. Let's do ac. I don't know how to. Okay, I need to like do this a little bit better. I think. No, I don't need it. I don't actually need it. Please, fuck off. Fuck off. Face, face, face. Fuck off. That's how some people speak. Math. Let's just call math. I don't know. It's mainly to like pirate books. I'm so smart for pirating books.
are so many calculus books out there, and it's really hard for me to say what my favorite is. But I think one of the best ones that I have is this one. It's Calculus by Michael Spivak. This is a legendary calculus book. Let me know in the comments below, what is your favorite calculus? I thought we would just... Hi, in this video.
Calculus pop
I thought we would just talk about this.
Advanced math heavy pattern recognition. Um, Best book for Calc in ML. Can I go calculus? Can I do that? Can I do that? Machine learning, mathematics for machine learning. No, I don't need a rigorous calculus or rigorous multivariable deep advanced. Okay. Okay, let's just. That's what I realized is that I need to like reason through some of this shit and like get good the normal way. Let's look at calculus, bro. If you guys have a thing for calculus, then I'm actually cooked. It's like, what the fuck is this, man? Who the fuck is reading from this bullshit? Calculus. I'm pretty sure people will just have it. You got to, right? No thanks, please. They actually have a PDF. Nice. Yeah, I'll take that. 4 pillars of jump. I'll take that. I'll take this. I can do that. Brother, this is the thing that I hate the most. For fuck's sake. Should I even do? I think I have to. If it tells me to like do something else, I'm gonna flip out. I'm gonna go. Everyone can see that too. That's... I don't know. Um, bro, I genuinely don't know. Like, what the. Bro, stop pissing me off. Can you, like, stop pissing me off? Let's collect books. Collecting books is low-key funny too. Burqa in your face! Religious police. I need to, like, compartmentalize this shit too. Scuba. I mean, come on, bro, you can take it. You need to take. Brother. Back to the sheet. First thing first, I eat your brain, brother. What the hell? How the hell, brother? How the hell am I supposed to study all of this, brother? This massive headache, brother. Uh, Spivak. Sounds like a chess player. Yeah, let's. Basic properties of numbers. Numbers of various sorts. Function, appendix, ordered pairs, graphs, vectors and conic sections and polar coordinates, limits, continuous function, three-hand theorem. These are all foundations. Bro, how long will it take me to get a field? So field is like the vector the construction of real numbers. Unit sequence okay. Bro, it's not that bad. It's actually not that bad. Let's basics, brother. I need big screen, brother. Probably not. I don't know. I need big screen. Chapter 1, Basic Properties of Numbers. The title of this chapter expresses in few words the mathematical knowledge required to read this book. In fact, it's a very short chapter and simple explanation. Okay, basic properties of numbers. Addition and multiplication, subtraction, division, solution of equation and inequality and factoring and other algebraic multiplication are familiar to us. Nevertheless, this chapter is not a review despite a familiar of the subject. The survey is what undertake will probably seem quite normal. It does not aim to present an extended review of the old material, but is condensed this knowledge in a few key fundamental properties and numbers. Some may even seem too obvious to mention, but surprising number, diverse, and most important facts turn out to consequence and other ones we shall emphasize. One of the 12 properties we shall study in this chapter, the first 9 are concentrated with fundamental operation and addition multiplication. So, should I do it? Don't want to, but my life would get better if I do. For the moment, we consider only addition. This operation is performed on a pair of numbers. The sum a plus b exists for only two given numbers, a and b, which may possibly be the same number, of course. It might seem reasonable to regard addition as an operation which can be performed on several numbers at once, and consider the sum 1 plus 1 plus and n plus number as a basic concept. Okay, it is more convenient, however, to consider addition pairs of numbers only, and to define other sums in the terms of this type. For the sum of three numbers a plus b plus c, this Maybe done in two different ways. One we can add a plus b, obtaining a plus b, and then we can obtain when we can add the number a plus, okay, we can obtain, okay, we know this. Can we get to the good part? Yeah. Brother, we know this. Easy shit, brother. Of course, this is equal to, you could write it in this way, of course. Easy. Okay, moreover, 0 is not equal to 1. Whoa. We're breaking new grounds over here. Associative, okay. So these are the laws. Associative laws for addition. So I got one wife. So me and one wife get on a relationship and another one tries to tag along. That is the same as, okay, me and Becky shagging and another woman joining us named Stacy. It's the same as me and Tracy shagging and another bird named Becky coming along. So that is the associative law, because this bitch Becky, or it doesn't really matter, she could be my main or side piece, who really cares, right? So it's basically the same thing. That's what I'm trying to say. So existence of additive identity. So 1 plus 0 is equal to 0 plus, okay, I'm sorry, a plus 0 is equal to a plus 0 plus a is equal to a. Of course, me with no money, me plus number of people arrested for Epstein Island in the USA is equal to number of people arrested in the USA plus me is equal to me. Of course, existence of additive. So what does this actually prove? Okay, existence of additive inverse. So I take one limb lengthening surgery minus inverse that a limb uh, decrease surgery. That is the same as taking a limb decrease surgery and a limb lengthening surgery. Both are equal to 0. That is the existence of additive inverse. Culminative law of addition. So this is the basic one. A plus B is equal to B plus A. We all know this. We probably said this when we were like a little kid, thinking this is the like deepest shit ever. You know, when you're like in third grade and you think this over here is like the pinnacle of mathematics, you get like scared by this. You know what I mean? But anyways, let's say existence of multiplicity, multiplicative. So a plus okay is equal as a. So 1 is not equal to 0. So we're basically proving 1 is not equal to 0 by multiplying. Wow. 1 is not equal to 0. Who would have thought? 1 is not equal to 0, yeah? I could have never thought. Never could have guessed. So A multiplied by 1 is equal to 1 multiplied by A is equal to A. Meaning 1. How do you even come to this conclusion? How do you even come to this conclusion? Makes no sense, bro. So anyways, existence of multiplicative inverse. Okay. A dot inverse is equal to A dot inverse. Okay, whatever. And for this, okay, we know it. 3 basic properties of the number which remains to be listed are concentrated with inequalities. Although inequalities occurs rarely in elementary mathematics, they play a predominant role in calculus. The notion of inequality, A is bigger than B, A is also, okay. Trigonometry law. Okay, bro. Ain't nobody got for time for that. Okay, this is the theorem. Brother, I can't. Come on. How do we... Bro, is this what mathematics is? Super. When are we going to get to the good stuff? Oh, we got some problems. Let's fucking do it. Let's fucking do it, bro. I don't want to... I don't want to use this. I want to use something else. To be honest, not really a big fan of like doing all of this bullshit. When does the good part start? It's like, this is boring, bro. No one wants to do this hard work. I gotta prove this. Come on. This is bullshit. Who the fuck enjoys this? Who the fuck enjoys this? You're lying. Neil deGrasse Tyson, okay.
I was on some random internet website several years ago, and it said that for most people who take calculus, calculus is the hardest math class they will ever take. And I thought, no way. There is no way, right? That's not true. There are so many more harder, more challenging classes after calculus. I mean, it's just the beginning of mathematics, really. I mean, there's so much more. There's so much more math. But then I read it again. For most people who take calculus, calculus is the hardest math class they will ever take. So it's talking about the people who take calculus. And that's true. It's true. I say this from experience, from teaching thousands of students and tons of calculus classes. It's true. Most students who take Calc 1...
Bro, why are we getting a Jewish guy? Oh, why are we getting a Jewish guy, bro?
Need to be a great physicist applied to physics.
I think the mathematical skill required today is so high. You have to be a world-class mathematician to be a successful theoretical physicist today. And it's not, you probably need other skills too, intuition, lateral thinking, and so on. But without just top-notch math skills, you're unlikely to be successful.
Need to be a great physicist applied to physics.
I think the mathematical...
One of the first videos I made on this channel was about
talented students. I've seen the fear of calculus actually make students change their career choice. It shouldn't be like that.
Math is not just meaningless formulas that popped out of nowhere. Even though you might not be able to see it, it's everywhere in our universe. Among the realm of mathematics, there's one particular field described by the Nobel-winning physicist Richard Feynman as the language of God, calculus. Scary, huh? Well, it's basically just a description of changes in our ever-changing universe. Normally, when we talk about changes in stuff, we talk about the difference in the amount of stuff after the change. Well, we can also talk about how fast something changes, the rate of change, how much something changes.
Let's look at the calculus flow chart. I think that would okay. Is it an infinite series? No. Can it be written as a type of recognized or broken down into pieces that we recognize? Yeah. Finite geometric series. So we got this one, and finite binomial series. So it is some sort of a Gaussian kind of stuff going on. Sum of conservative integers. I think this is the Gaussian formula itself. And no, but terms are bounded. Add them terms to find the value. Okay, we need to add all of them up to find the values. Okay, cool. What are the terms approaching to 0? Yes. If it is yes, it is is an alternating series. Yes, limit is equal to 0. Okay, it is approaching 0, and we're trying to like find it. So if it is, are the terms positive and decreasing, or we can rewrite it as such? How does a math test look like? I don't know. How does a math test paper? I actually don't need it. I just do it because I like torturing myself now and then. Briefly, and it's bro. Vaguely heard of all of these terms, but it's like, how the like this is all too complicated, bro. Too complicated. I can't. A tiny break can. Neural networks. Mm, you're kind of fat, bro. You're getting skinny fat. It's not good. It's not good, bro. It's not good. Yeah, let's look into this. What is neural net? It's just like a bunch of functions going in. I don't know.
To the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again, some number that's between 0 activations in the next layer. It's meant to be loosely, and I don't mean this specific loop of pixels, the hope would be that any generally loopy pattern towards the top. So maybe one of the connections between our neuron and the neurons from the first layer. These weights are just, do is have some negative weights associated with the surrounding pixels.
Brother, what even is this video? I don't know. How does AI images and videos work? Yeah, I don't know. Math behind it
Over the
all.
last few years, AI systems have become astonishingly good at turning text prompts into videos. At the core of how these models operate is a
and for by mathematics for
Yes, thank you. And it's a real pleasure to follow this T, or in the number of parameters, which we call D. And this is something that was observed in around 2020, and not only by this paper, but by several other papers. And then there are a good amount of theoretical works proving that in various models, indeed, there are scaling laws. But the main point is that any but in the end, that's what people do. So what will happen is the model is trained on the internet, on the pristine internet from 2020, perhaps, and all is good. But then as time passes,
Bro, these niggas are cracked. Niggas are cracking lead, brother. What even is this? I don't know. But why is all of these tryhards doing all of this shit? I don't understand it. It's like, bro, chill out. Take a chill pill, mate. It's like, it's too much math. Too much like, it's operating in like 20 I don't understand it. I don't understand it, bro. I don't understand. Who understands this shit? Genuinely. Who here, like, yeah, I understand that. Bro, I don't even know what math for ML. Who understands all of this?
In this video, I'm gonna be...
Bro, I don't like this bitch. Math for ML. They don't understand the things I say on Twitter. Oh, my brothers, Christians, brother, hallelujah. Brother, hallelujah. Brother, hallelujah. Bro, I don't understand it. Like, what the fuck is LLM? What is all of these, bro? LLM? What is
And then think about how our models are trained. What are they doing?
What is LLM? What does... Okay, I understand how the tokens work. That's something. I understand how all of that works, but what the fuck is this? Okay, I understand all of that. Engineering behind... Bro. Who understands all of this? Genuinely. Math behind it.
Nobody has sat around. If you think about us humans, nobody has sat around labeling the data for us. Our brains. If you think about us humans, nobody has sat around labeling the data for us. Our brains, over evolutionary time, have learned about patterns that exist in the natural world. So given that that's how nature has done it, there's no reason to expect that the machines that we build are also not going to be powerful just because of that technique. I honestly, sincerely believe that we can't leave the building of these AI systems to just the practitioners. We need more people in our society, whether they are science communicators, journalists, policymakers, just really interested users of the technology, but who have some math background, or people who are just willing to persist and learn enough of the math to make sense of why machines learn. It's only when we understand the math that we can point out that, hang on, these things are not reasoning in the way we think we are reasoning. It's because the math clearly shows that what's happening right now is that these machines are just doing very sophisticated pattern matching.
Welcome back to MLST. We are interviewing the author of this book, Why Machines Learn, by Anil Anathaswamy. Anil was flying on July the 17th on his way to India. He had a stopover for about 12 hours, and I invited him to come and do an MLST interview. Unfortunately, there was a schedule clash. I thought he was going to be here the day before, maybe the day after, and I had to get my good friend Marcus to pick him up from the airport, take him over to the studio, and ask the questions on my behalf. So I'm going to re-record the questions. I mean, unfortunately stuff like that happens, but very, very pleased that I managed to get the main man in the studio, even if I wasn't there. So yeah, Why Machines Learn. What is this all about? It's a really interesting kind of pedagogical history of the field, but going into some of the underlying mathematics behind many of the approaches in machine learning. Anil is a veteran science writer. You should look at some of the other books he's written. He's really, really good. The book was written beautifully. I enjoyed reading it. Oh, by the way, he signed it as well. Pretty cool, eh? I hope you enjoy the conversation with Anil. Can you introduce yourself?
My name is Anil Anathaswamy. I'm a freelance journalist. I trained as a computer and electronics engineer. I did my bachelor's in India and my master's at the University of Washington in Seattle. Worked as a software engineer for a few years before I started feeling the itch to become a writer. And at some point I figured out that the two things I love, science and writing, could be combined, and that I could actually become a science journalist or a science writer. So I went back to school, studied science journalism, came to London to do a internship with New Scientist magazine, was with them for 6 months doing the internship, and that eventually led to a staff position. I was staff writer in London, became physics news editor, then became deputy news editor, and and wrote for New Scientist for a long time. And while I was doing that, I was also working on. I started working on my books, and the first one was called The Edge of Physics. It's a travelogue based book on cosmology and astroparticle physics, and each chapter is essentially a piece of travel writing where I go to some really extreme locations on Earth, like the Atacama Desert in Chile, to Lake Baikal in Siberia in peak winter, to places like Antarctica, all the way to the South Pole. And so that book explores essentially extreme physics. And the second book is called The Man Who Wasn't There, and that's an exploration of the human sense of self. So when you ask the question, who am I, you kind of get answers from theology and philosophy. In this book, I tried to answer that question from the perspective of neuroscience and neuropsychology. The third book was Through Two Doors at Once, which is an exploration of, it's essentially the story of one single experiment called the double slit experiment, which is an extremely mysterious experiment to explain with our standard way of understanding the world. And yet it's very illustrative of what's happening at the quantum mechanical level. So it's really a story about quantum mechanics and quantum foundations, but told through the lens of one experiment, all the variations of that experiment done over 200 years. And finally, my last book is the book on machine learning. It's called Why Machines Learn, and it's about the mathematics that underpins modern artificial intelligence.
What inspired you to write about the elegant mathematics of machine learning? And can you give an example that you find extremely exquisite?
I'm writing about particle physics or cosmology or neuroscience. I never felt like that was something I could do as personally. It was more about understanding the science and writing about it. But over the last few years, I found myself writing more and more about machine learning. And given my software background, given that I used to be a software engineer, every time I would write stories about machine learning, I think the software engineer part of me woke up. I would look at those stories and get this desire to actually get back into doing a little bit of coding to actually understand this technology from the ground up. So about 5 years ago, I did a fellowship at MIT called the Knight Science Journalism Fellowship. And as part of the fellowship, I decided to teach myself coding all over again. So 20 years after I had stopped doing any programming, I literally went back to the computer science 101 kind of classes, sat with teenagers and taught myself Python programming and PyTorch, and started building some very rudimentary machine learning systems, one or two small things that I learned how to do. And as part of that exploration of trying to build a deep learning system, a deep neural network based system, I got more and more interested in understanding the kind of mathematical underpinnings, the basic theory behind machine learning. And towards the end of my fellowship, COVID happened. We were all stuck in our apartments, and I spent a good 6-7 months basically stuck in an apartment by myself, both in Boston and in Berkeley, California, listening to all these machine learning lectures over and over again, teaching myself essentially. And at some point, I started realizing that the mathematics that underlies machine learning is quite beautiful. And I think then the writer in me woke up. These ideas to my readers. So that's how the idea for this book came about, Why Machines Learn, which is essentially really about some of the conceptual mathematical principles that underlie modern artificial intelligence. Yeah, and regarding, what is elegant about the mathematics of machine learning, a lot of people will say, machine learning is, mainly about knowing calculus and linear algebra and probability and statistics. What's particularly elegant about that? And I'm not talking about those subfields of mathematics. For me, the beauty and elegance that I found when I was learning about machine learning had to do with some of the theorems and proofs that I encountered. Like, for instance, if you go back to 1959, when the first artificial neural networks were being designed, there's a proof called the perceptron convergence theorem and its proof, and it's a very, very simple proof just based on linear algebra. And it was while listening to a professor explaining that to his students in Cornell that I think fell in love with the subject. I really felt like, okay, this is something I really need to tell readers, that there is something wonderful.
Okay, let's pirate his book. It'd be super cool if my TV remote works. I could just read it. Fucking bitch, man. Fucking. Just. It's like, how many batteries do you need? You're just. How many batteries do you need? Fucking goblin. Taking all of my batteries. No one though. That's my work. Fuck. It's just insane how many battery it takes. I don't understand it. Literally makes no sense. I had a dream about I need to like get some battery supplies or some shit like that. I don't get it. Like I literally don't get it. The fuck is with this battery shit? How long does it take to read this book? Take to read this book. Question mark, I understand. I understand, bro. Some books about deployment and neural network describes the underlying mathematics, while other describes the social history. Yes, based on what is shown. Okay. This from Social History is a masterpiece. The author is very good in explaining the mathematics in the way that makes available to people with only rudimentary knowledge of the field. But he is also very good at very good writer who brings the social history of life. Is he like talking about you? Okay. Why you like? Why do you want to like glaze yourself, bro? Let the book talk for itself. Jeet. After just a few readings, why machine learning, you will feel your own sympathetic weight getting updated. By the end, you will achieve your own version of deep learning, with deep learning pleasure and insight along the way. New York bestseller author of Finite and Power. Who are these people? Physicist, New York Times bestseller. Okay, cool. Artificial intelligence professor. Okay, cool. AI pioneer, entrepreneur, and parent classifier. Cool. Professor. Okay, I will like sucked your dick enough. Fucking faggot. Anyways, let's just like look into it. So I don't care about the prologue. Desperately seeking patterns. When he was a child, the Austrian scientist Konrad Lenner's enamored with tales of the book called Wonderful of Adventure and Nils. The story is about a boy with a wild geese, written by Swedish novelist and the writer of the prologue Simon Leon, to become the wild goose. Unable to indulge in the fantasy, young student settled for taking care of an old duck his neighbor gave him. The boy, delighted, the duck began following him around. It had imprinted on him imprints reference to the ability to make animals, to able like geese, goslings, to form bonds with the first moving thing that they see upon hatching. So were able to go on become etiologist and would pioneer the studies of field of animal behavior, particularly imprinting. He got a duck to imprint on him. They follow him around as he walked, swam, and even paddled away the canoe. He won the Nobel of Physiology and Medicine, jointly with fellow etiologists Carl Won and Nicholas Stemmel. These three were celebrated as a discovery of concerning organizing influence social behavior patterns. While etiologists were discerning them in the behavior of animals, the animals were detecting patterns on their own. Newly hatched ducklings must have ability to make out telepathic properties and things that they have moves here. It turns out the ducklings can imprint not just on the first living creature they see moving, but also innate things as well. Mallard duckling, for example, can imprint on the pair of moving objects that are similar in shape, color. Specifically, they imprint on the rational concept embodied by the objects. So, if upon birthing ducklings see two red objects moving, they will later follow this object in the same color, but not two objects in different colors. In this case, the duckling imprint the idea of similarity. There are also the show of discernment and dissimilarity. if the first moving object ducklings are seen, for example, is a cube and a rectangle prism, they will recognize this object have similar shape and will later follow the two objects in different shape, pyramid and a cone. For example, they will ignore the two objects and have the same shape. Ponder this for a moment. A newborn duckling with the briefest exposure of sensory stimuli detects a pattern in what they see from abstract notion and similarities and dissimilarities, and will recognize those abstractions and stimuli. They will later act upon them. Artificial intelligence researcher who would offer a norm and like to know just how ducklings pull this off. Yeah, true. While today's AI is far from being perform some such tasks with ease and efficiency and of a duckling, it does have something in common. The ability to pick and learn things in pattern and data. Researchers provided Rosenbell perceptron will find the pattern hidden in the data of a finite time of research, but different perceptron will cover upon the solution without fail. Such certainties ow
Simple proof just based on
as we plan. Let's start examining this table. We have 1x, 2x, y. Okay, 1 divided by I don't see a pattern here for each row on the triplet values, and why there's a simple hidden pattern in this data. In each row, the value y is related to the corresponding value 1x, 2x. You see, you can spot and reading for so are we like, it's like a multiplication plus addition thing? So multiply them and add them, multiply them and add itself. Okay. 1, 2 into and add them. Okay, I think I got it. The small point about notation, we're going to dispense with the multiplication x sign between the variable and the constant. For example, we write. Okay, okay, bro. Could you not pick a different? Ideally, we should write with these variables subscribe, but we will dispense with subscript 2 unless it becomes absolutely necessary to use. Some purists will cringe, but this method I have to keep our text curated. So keep this in mind. If the symbol x is followed with such a digit or 2, it gives us 2x. The entire symbol, okay. So what did we find? We found this. Oh. No, I actually don't want to do this. Fuck. I actually don't want to do this. Oh my god. First out of, I just want to like read about the history or some shit. Bro, I'm done already. Fuck this. I actually don't want to do this, bro. Fucking. Who cares, brother? Let's hear what he has to say.
Linear.
I'll put you on save though. How can I save him? How can I save this nigga? VLM, Vision Language Models. Let's see a playlist. Can a nigga get a playlist? What is this? Contrastive language image pre-training, clip and version.
Greetings, my name is Samuel, and in this video I will aim to provide a digest of contrastive language image pre-training, or CLIP as it is better known. This method was introduced in the paper Learning Transferable Visual Models from Natural Language Supervision by Alec Radford and co-authors, published at ICML 2021. Here is an outline of what will be discussed. We will start out with motivation. We will then discuss the data and method underpinning CLIP, and a range of experiments.
Hey guys, today we are going to implement VLMs, which stands for Vision Language Models, from scratch. What Vision Language Model does? VIT from scratch as well. So the things we have now. And number of embedding is not a part of the sequence. And now we will put the tokenizer to self, basic in
Adversarial robustness and compression. What the fuck is? Yeah, what even is this? Like, I don't, like, I try to understand it, but it's like, don't get it, bro.
The theory and code for vision transformers in 15 minutes. This is a quick guide to give you all the details you need to know. At the end, I also quickly talk about some differences between CNNs and vision transformers. Let's get started. Here you can see the transformer architecture, which you might or might not.
Moondream AI, powerful VLM on brother.
There is a new powerful vision language model. This is Moondream 3. This is.
It's not gonna work. We already know this, bro. Computer vision from scratch. Is brother from MIT? No. Then why the fuck would you wanna market yourself that way?
Hello
Talk to me, boy. Talk to me.
Hi, my name is Manish Gupta, and in this video, I'm going to talk about vision transformers. Vision transformers is a very old model, but I thought I would just record it because it is one of those basic initial models which showed that you can actually use transformer models also for vision tasks. So what is vision transformer model? Well, it's a model which basically motivates the usage of transformer for vision tasks. Many other models have now come up which basically use this as the base backbone. Right. So this is the standard architecture of a vision transformer model. It is also called as VIT popularly, right? So the idea is that for any kind of vision classification tasks, for example, let's say image classification.
How do I get the tutorial on vision foundation models? Okay, I don't know.
Good morning, everyone. So I hope you all had coffee and get ready. It's 9 a.m. We have a lot of
Location, Seattle Convention Center.
good stuff for today. So let's get started. For the past 4 years, we have been organizing tutorials on vision language pre-training and more recently on vision foundation models. This year is no exception. I'm Li Jun Wang, and I'm honored to kick off the event today. If you are interested in the history and the background, I encourage you to check out our previous tutorial on the website.
In the previous,
We have also
shut the fuck up, please. Vision learning models. I don't know. What even is that? What even is that?
Important fundamental step in your knowledge as a machine learning engineer. What is equally important is to understand how to use large language models in practice, how to apply large language models in real life scenarios, and how to build and deploy applications using large language models. Hello everyone, my name is Dr. Raj Dandekar. I graduated with a PhD in machine learning from the Massachusetts Institute of Technology in 2022. And now we are on a mission to make artificial intelligence accessible to all. I'm making this video as the introduction video or the first video in the new series of lectures which we are launching, and that's in the field of hands-on large language models. We have covered a huge number of lectures in this series called Building Large Language Models from Scratch. There are around 35 to 40 lectures in that series, in which we introduce the nuts and bolts of building a large language model, building your own chat GPT completely from scratch. While that is incredibly useful and a very important building block and a important fundamental step in your knowledge as a machine learning engineer, what is equally important is to understand how to use large language models in practice, how to apply large language models in real life scenarios, and how to build and deploy applications using large language models in industries. The whole aim of this lecture series which we are starting is to show you how large language models are actually used in practice and to develop a huge number of applications with LLMs. We will follow the approach which is the trademark, I would say, of our teaching style, and that is in-depth content with a lot of attention to detail. So the content will be very much detailed, and at the end of this series, you will get a fundamental understanding regarding building large language models, deploying large language models in production. And along with the theory of LLMs, which we have covered in another lecture series called Build LLMs from Scratch, this lecture series will teach you the applications, and hence with both of these skills, you will be a very strong machine learning and a large language model engineer. Similar to all the playlists which we create, this playlist will also be very comprehensive. It will probably include more than 25-30 lectures and will cover a wide range of applications in large language models. So let's get started with our first lecture of this series. Hello everyone and welcome to the first lecture in the hands-on large language models series. Before we get started with the lecture itself, I want to show you the reference book which I'll be following throughout this lecture. So last month, an amazing book on this topic came out on O'Reilly, and it's written by the authors Jay Alamar and Martin Grutendorst. These are amazing researchers and engineers in the field of large language models, and I've been actively following Jay on LinkedIn for a very long time now. The content written by Jay is one of the most detailed and very illustrative content which I've come across. So when I saw that this book is getting launched, I was incredibly excited and it did not disappoint me. So if you look at the table of contents in this book, this is exactly what we'll be covering in this lecture series. So the book itself is divided into 3 parts. In the first part, we will understand large language models, intro to LLMs, tokens and embeddings, and looking inside large language models. In the second part, we'll look at pre-training large language models and how to use the pre-trained large language models. So here is where the application really comes into the picture. We'll see several applications such as text classification, text clustering, topic modeling, prompt engineering, advanced text generation techniques and tools, semantic search, retrieval augmented generation, and even multimodal large language models. Multimodality is extremely important because large language models don't just deal with text, they deal with several other modalities such as sound and videos as well. So part 2 covers the bulk of this book, and these are all the applications which we'll be understanding in this lecture series. However, the book does not stop here. There is also part 3. Let me go back. Yeah, there is a part 3 over here in which there are 3 things which are covered: creating text embedding models, fine-tuning representation models, and fine-tuning generation models. There is a difference between representation models and generation models, as we'll be covering subsequently in these lectures. But for now, just know that we'll be exploring fine-tuning in the third part of the model, in the third part of this lecture series. And in the second part of this lecture series, we'll see how to use pre-trained models for performing several applications. Fine-tuning is another training stage which is built on top of pre-training. That's equally important, but we should know when to use a pre-trained model and when to use a fine-tuned model. With this background in mind and with
Is clip still used?
Everyone, in this video we are going to cover the clip model proposed by Hi everyone, in this video we are going to cover the clip model proposed by OpenAI. Contrastive Language Image Pre-training. The main idea of CLIP is based on natural language supervision. So they use self-supervised pre-training based on the natural language as the learning signal. They pre-train their model on a very large dataset of image-text pairs that they collected from the public domain.
This is why, but it's no longer the most cutting-edge vision learning model in research. Prototyping model, educational.
CLIP model has several use cases, one of which is zero-shot travel.
Okay.
Transfer. So in this video, we will see more details on how CLIP is trained and evaluated. First, let's discuss the motivation for the natural language supervision in the context of image representation learning. So far, most computer vision models are trained in a supervised manner, but obtaining the labels and annotations for supervised training is usually expensive, and therefore, there are limited amount of data available for supervised learning. On the other hand, there is unlimited amount of raw text that can be used for natural language supervision. So to summarize the advantages of natural language supervision, first is that it's easier to scale compared to the supervised training, and second, with natural language supervision, you automatically connect image representations and natural language representations, so this enables several potential applications for multimodal image and text data. For pre-training the CLIP model, they collected a dataset of 400 million pairs of images and text, and they called this dataset Web Image Text, or WIT. For building such dataset, they gathered 500,000 queries based on all the words in the English Wikipedia that were repeated at least 100 times. As a result of this, they got image text pairs like this example shown below. Also, in order to balance the dataset, they included up to 20,000 pairs per query. Natural language supervision for image representation learning is not a new idea. CLIP is actually inspired by these two models, Virtex and Convert, that both share the same motivation. Since obtaining labeled data in specialized domains such as medical data is difficult and costly, so instead they want to pre-train using natural language supervision with unlimited textual data. So first, let's see these models briefly. The Virtex model is composed of a visual backbone and a textual head as shown in this figure. The visual backbone extracts features from the input image, and the textual head receives the features from the visual backbone and predicts the caption word by word. After pre-training the Virtex model, this model can be transferred to downstream tasks. However, the major drawback of this approach is that it is difficult to predict the exact caption, since there are various possible captions that can go with an input image. So as we'll see, Convert and CLIP models, they both opted for a different approach. The Convert model is specifically proposed for medical images, where getting the supervised labels for images requires domain experts, and therefore it would be very costly. Two example images and their description is shown on the left, and the sentence that is randomly sampled from the corresponding medical document of each image is shown below them. So Convert tries to learn image representations using natural language supervision. The first difference between Convert and Virtex is that here, the visual and the textual networks work in parallel, in contrast to Virtex. For training this model, they use contrastive loss that tries to increase the cosine similarity of representations of images and text from the correct pairs. Now, moving back to the CLIP model, we saw two different ways of natural language supervision. Virtex tries to predict the exact caption, while Convert uses a contrastive loss that tries to maximize the similarity of corresponding representations. As we said earlier, predicting the exact caption is difficult. Therefore, CLIP follows the approach of Convert instead. So given a batch of image text pairs, CLIP. Here is the diagram and the pseudocode for training CLIP. The visual and textual encoders work in parallel, similar to the Convert model. Feeding a batch of paired images and text, the visual encoder outputs representations I1 to IN, and the textual encoder gives T1 to TN. We normalize these representations with L2 and perform dot product between the normalized image and text representations, and as a result, we get a matrix of similarities as shown here. Note that the two labels is on the diagonal of this matrix, so we can construct an array of labels for correct pairings simply with this np.arange function. Then we compute the cross entropy loss on this matrix, once for the dimension 0 to get the loss for the visual encoder, and then on dimension 1 of this matrix for the loss of textual encoder. And finally, we take average of these two losses. Now let's look at the architectural details of CLIP. For the image encoder,
Brother, multimodal LLMs study vision transformers.
Hello everyone and welcome to this lecture in the hands-on large language models series. Today we are going to start looking at an extremely useful aspect, which still feels very magical to me, and that is related to multimodality. The name itself, multimodality for large language models, it's a bit contradictory, right? Because large language models already has the name or the word language in it. So when we deal with textual information, it's fine because we generally associate language with talking, speaking, text. But what has been very surprising since the development of large language models has been that there have been a huge number of advancements which have been made in different modalities as well. What are these different modalities? These different modalities involve code, image, and audio in particular. There have been a lot of advancements in the video space as well, but for the purposes of today's lecture, we are mostly going to look at image modality. In particular, we are going to learn in detail about a new type of architecture which is called as vision transformer. But before directly jumping into the subject, first I want all of you to appreciate the beauty of this, the beauty of science. Who have thought that large language models can be extended to the vision space? So for example, if I go to ChatGPT right now, and if I use this picture of a cat, and if I say, what do you see in the image? ChatGPT very accurately responds, this image shows an orange cat with a curious expression. The cat is sitting on a surface, wearing a collar with a bell. How does it work? How does ChatGPT know what's there in this image? Similarly, you can go to Claude and you can ask a similar question. What do you see in the image? And very similarly to ChatGPT, it answers, this is an adorable orange cat with a sweet expression looking directly at the camera. So not only can we detect what is there in the image, it's not a simple, it's a cat. The language model, as you can see, answers as if it's a human who has been asked to see what's in the image. Because if a human is asked, hey, tell me what's there in the image, we will not just say it's a cat, right? We will use our language abilities to give a much comprehensive description. And since large language models already have language abilities, once they start detecting images, once they start working with images, it leads to a whole new powerful capability for the large language model. Now keep in mind that this is different than image generation. In image generation, we give a text and we create an image. That is not being covered in today's lecture. Today we are mostly going to look at, if we pass an input as an image to a large language model, how does it know what to do with that input? Until now we have seen everything related to text. But what about images? How can we extend large language models for images as well? Researchers usually take on these problems which look impossible, right? And then they make it possible. One such example of this is this paper. An image is worth 16 by 16 words. This is the main paper which we are going to look at today. Now if you copy this and paste it in Google, you'll see that this paper has more than 50,000 citations since 2020, which is a huge number. I would say it's in the same league as the Attention is All You Need paper. It was a pretty revolutionary paper which demonstrated that transformers can be used for image recognition. The same transformer architecture which we have looked at before can be extended a bit to process images as well. So this lecture is a tribute to all those researchers who usually think that difficult things are possible and then they embark on this mission. So let's get started. First of all, let's look at the definition of multimodality. So models which can handle both text and images are called as multimodal, right? And this can involve other modalities also like code, audio, video, etc. So another more comprehensive definition is that models that are able to deal with different types or modalities of data, such as images, audio, video, sensors, are said to be multimodal. There is not a very clear definition for what multimodal is, because if you see code is not a different modality, it's just a different type of data, but even that is bucketed into the broad term of multimodality. Another thing to mention is that some language models are able to take in image as an input, but they cannot project or cannot produce image as an output. They can only produce text as an output. Even these models are said to be multimodal because at least they are taking different modalities as input. But as we know, ChatGPT can take both text and images as input, and it can even produce an image as an output. Okay, so the main component which we are going to look at in today's lecture is transformers. And how are we going to adapt transformers for vision? So before we go to that, let me give you a quick overview of how do transformers actually work in the first place. So for that, I'm going to actually take this diagram as a reference. It's from the book Build Large Language Models from Scratch by Sebastian Rashka.
I'm just going to copy this diagram over here and I'm going to paste it on my Miro so that I can explain transformers and how they traditionally work for text, right? So, okay, so this is a typical transformer architecture, which you can see, which is implemented in GPT-2. So you can think of this as representative of how transformers deal with text. What happens is that we have an input sentence. Let me change my color to orange maybe. We have an input sentence, every effort moves you forward, right? This is the sentence. And the goal is to predict the next token based on this sentence. What the transformer does is that, or rather, before going to the transformer architecture, first what we have to do is that we have to take this text and we have to break it down into individual tokens. So the first step is the process of tokenization. And for the sake of simplicity, I'm going to assume that one word is one token. This is not the case usually because GPT uses a byte pair encoding tokenization scheme which has subwords as tokens. But let's assume for the sake of simplicity that the different tokens are every, effort, moves, you, and forward, right? So the transformer never processes the entire sentence at once. It breaks the sentence into tokens.
Okay, we got a VLM action going on. Semantic. So, I mean, yeah, I need to look into clip and what it actually does. Okay, create text embedding models. Yeah, that thing right there. I think that could kind of help. I need to like who else? Self-supervised learning. Yeah, I should do open clip. I mean, I did have this thing, vision language models. So, things should be out anytime. Bro. La 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 la. Na 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 na. Okay, I do have that, so best books on 3D reconstruction. Just collecting books. Bro, they're not doing books. That's stupid. Just have to like do it. I think everything is there already. He is seeing some results, and compute. No, fucking bitch. Graph convolutional neural network, graph machine learning. Holy shit. Going on the deep end. Fucking advanced book. I think I did have this though, didn't I? Looks like I didn't. This book is about and explores how graph model transform computers, extended tradition to handle graph-like structure where relationship between elements and nodes matter much more than the element themselves. This allows. Bro, no way. I just struck gold. I struck gold with this shit, nigga. Bro, he never thought of this. Just a genius. The fact that no one thought of this, it's so fucking cool. Naturally model irregular. What are the Am I over engineering this shit without writing a single line of code? Probably. Role of graph abstract graph reported concept in observed computation for transforming, understanding, and modeling graph structured data. They have unique capabilities to capture intricate relation among the visual content that goes beyond the traditional and the usual convolutional network. It also empowers computers to observe the interpret and complex interconnection between the elements in image, which enhances the depth of the nuance of the visual data analysis. As revolutionary as the semi-computer vision genus are poised to transform vision industries, unleash new frontiers in the visual information domain analysis and interpretation. The multifaceted application promised to reshape the landscape of computer vision. Keyword: graph convolution neural network, computer vision, graph structured data, visual data analysis, visual information analysis. Introduction. Rapidly. Oh fuck.